Hello, let's do some examples. The limit as x goes to 0 of 2x over 3x plus the cosine of x. Remember, the limit of the sum is the sum of the limits. And so that's just limit the separate limits right here and here. Now, the limit x goes to 0 of 2x over 3x, that's just 2/3. Now, really, at x equals 0, we get 0 over 0, which is undefined. So we're not continuous at x equals 0, but the limit exists, and that's all we care about here anyway. So that limit is 2/3, and from the continuity of trig functions, we're going to go ahead and assume that trig functions are continuous and polynomials and all that. So that's going to be cosine 0, which is 1, and 2/3 plus 1 is 5/3. And guys, by the way, let me just go ahead and come out and say it. We're going to go ahead and assume that trig functions and polynomials and inverse trig functions on the appropriate domain and rational functions and roots where the domain is appropriate and all the like exponentials and logs where the domain is appropriate, we're going to assume all this is continuous without proof, okay? So just go in and just take it for granted. Like e to the x, the limit as x goes to 5 of e to the x is e to the 5th. Or the limit as x goes to 5 of the natural log of x is the natural log of 5. You can take that for granted. Likewise for rational functions, for polynomials, for roots, as long as you're in the domain. For just about all the run-of-the-mill functions, trig functions, inverse trig functions, radicals. Well, that is root. Radical is a root. Never mind. What else? But yeah, take it for granted. You can always take it for granted, okay? So here, now the limit as x goes to negative infinity of this fraction right here. Now, we can't just throw the limit up here. We can't just say the limit of the quotient is a quotient of the limits yet. The quotient of the limits would actually get us in trouble. But what we got to do is divide by the term with the highest exponent, which is x cubed. So divide the numerator and denominator by x cubed, and then break up the fraction arithmetically like that, each guy over x cubed. And then divide by x cubed by the law of exponents. You subtract 3 off the original exponents. But what that means is, like, 3 minus 3 is 0. That's gone. That's just negative 11. And then 3, it's 1, let's just do 3 minus 1 with the understanding that 3 is on the bottom. That would put x squared on the bottom. This x would cross cancel division-wise with one of these x's down here. Remember, x cubed is x times x times x. So that x cancels with one of these x's, and you just get 10 over x squared. And in a similar fashion, now minus 7 over x cubed, that's not going to change. There's nothing we can really do with that. Now 8x cubed over x cubed down here, we're in the denominator. That's just 8. And then 5x squared over x cubed, that's just 5 over x when you simplify it. X over x cubed is 1 over x squared, understood 1 over x squared when you simplify it. And then 2 over x cubed, well, the minus sign's there, but 2 over x cubed, that stays put. The minus 2x cubed, we just leave it there. And now, okay, we can do the limit. The limit of this quotient really is the quotient of the limits because nothing goes to infinity or 0. So we're in good shape. So we bring the limits up. We get let me go down here if it will ever get down there. Oops, it's misbehaving on me here. So the limit of this quotient is the quotient of the limits. It's going too far down. It's going haywire on me. So the quotient of this limit, now we stay with the quotient of the limits. We go even further. Now the sum and difference of the limit of the difference is the difference of the limit, and the sum of the limit is the limit of the sums as long as all things exist. So we just break it up like that. And then we just get, now the limit as x goes to negative infinity of neg 11, that's just neg 11. Neg 11 doesn't care. It's just a constant. And the limit as x goes to infinity of 10 over x squared, that's 0. Well, we can yank out the 10. I go ahead and yank out the 10. I yank out the 7. But that's just more showing off. These limits are going to be 0 because as x gets really big, and you know what? All these things that I've said for this example would be true if x was going to positive infinity. It really doesn't matter in this example which infinity we're going to, but I wanted to pick one, so I'll pick negative infinity, okay? But anyway, the limit as x goes to either infinity, in my case negative infinity, of 10 over x squared or any constant over x squared is 0. Because as x gets really big in either direction, 10 over x squared is getting teeny tiny. And then likewise, all the more teeny tiny for this guy. And even 5 over x is still getting teeny tiny. So these zero out. I yanked out the constants, but that was just more show and tell. But the point, these limits are going to be 0. So we're just going to get zeros, and we're just going to get negative 11 over 8. The negative 11 is my only survivor upstairs. The 8 is my only survivor downstairs. So I get negative 11 eighths. And the negative was up there with the 11. I just yanked it out to the side by arithmetic. So notice something, guys. We have just found a horizontal asymptote. So y equals neg 11 eighths is a horizontal asymptote of f when f of x equals the original function, this guy right here that we had in the beginning. Okay, now as an exercise, you go in and you do this. That'll be one of your early exercises. I'll let you go in and do this for yourself. See if you get 1/2. You'll wind up with 3/6, but that'll reduce to 1/2. But I want you to go through all the motions. I don't want you to just take it for granted. I want you to go through showing these steps. Don't do shorthand. I want you to go through and show this, okay? But anyway, that's for you to do. And here I come out and say it. We're going to assume continuity. Oh, absolute value. I forgot about that. We're assuming continuity for absolute value as well. And powers, I forgot. How could I forget about those? But yeah, we're assuming continuity for those. But anyway, all these good guys here, we're assuming continuity for absolute value, powers, the whole Monty. If I forgot to say anything, it's here. So I forgot to mention some of these guys earlier. So all this, we're assuming good. We're assuming continuity, all that. Now, for rational, there is a caveat, a catch-32. Continuity is only good if we're in the domain. Like if f of x equals 1 over x, we can assume continuity at, let's just say, x equals negative 7 or anywhere that's not 0, but we can't assume continuity at 0 because 1 over 0 is undefined. In fact, f of x goes crazy as x goes to 0. But anyway, so we're not, f of x is not even defined at 0, let alone if f of x equals 1 over x is not even defined at 0, let alone continuous at 0, x equals 0. Okay. So here's some examples. The limit as x goes to 7 of x squared is just continuity. We plug 7 into x by continuity, and we get 7 squared, and that equals 49. Limit as x goes to 36 of radical x by continuity that is assumed for roots. You can just throw 36 into here. Square root of 36, remember, is 6. Limit as x goes to 5 of this guy right here, continuity. Just plug 5 in, and there you go. There's nothing much you can really do with this guy. And the limit as x goes to any real number c of the sign of negative x. Remember, from trigonometry, you can take the negative out, and by the rules of limits, you can take out the negative out here to the side. You can think of that negative as a multiplier, a negative 1 multiplier. So like you can think of it as the negative 1 times the sine of x. The limit negative 1 times sine x is negative 1 times the limit of the sine of x. But I didn't bother putting the 1 in front here, okay? And the next idea is extremely important. I'm going to save it for the next video. It's huge. It's kind of a funny time to leave off, but I need to because composition is just that important. Thank you guys. I'll see you on the next video.